Hello everyone, welcome to part 4, module 2, computer network. So what we were discussing is the data link layer design issue, that is framing, and the two ways of doing it by means of that byte count method and attaching a special flag byte at the beginning and end of the frame. And when the same flag byte occurs in the original data, we overcome that by means of attaching the some special escape bytes in between. Now the third technique what we have is using having that framing with the help of flag bits with the bit stuffing, in the sense we will be, instead of that flag byte that we discussed so far, here we will be using some special sets of flag bits that identify the start of a frame as well as end of the frame. So now if the same pattern is occurring in the original, as part of the payload or in the frame as a whole at any point, that pattern will be broken by attaching a special bit. So that is the whole idea. So the third method of delimiting bit stream gets around the disadvantage of byte stuffing. Byte stuffing, what is the problem there? If the same flag pattern is occurring in the original message, we will stuff an additional escape byte. Now if whenever that flag is repeating, whenever that escape byte is repeating, every time you have to attach that additional byte, and that is just a overhead which will be removed at the receiver side. So that problem, I hope you are clear about it, or please watch that previous video to get that to understand what is the disadvantage of byte stuffing. So to get around that problem, we have this concept. So framing can also be done at the bit level. So frames can contain an arbitrary number of bits made up of units of any size. So it was the technique was used in the high level data link control. This is another data link layer protocol. Just like we already seen that byte stuffing method is what we are using in the point to point protocol. Similarly, another data link layer protocol is HDLC, high level data link control. We may see this protocol in detail as it is highlighted in your syllabus. And in this HDLC, this is a technique that we are using for framing. So what we will do is, each frame begins and ends with a special pattern instead of that flag byte. Here we are using a special pattern. That pattern is something restricted. So what is that pattern that is particularly used in HDLC? It is 0 followed by 6 ones, then a 0. So 0, 1 1 1, again 1 1 1 and 0. So if you are reading it, means if you group 4 bits and you write the equivalent hexadecimal, the equivalent hexadecimal representation is 0 followed by 3 1, that is 7, then 111 that is E, 0 hexadecimal, that is 0x7E. That is a special pattern fixed in HDLC as a start of frame delimiter and end of frame delimiter. Now whenever the sender's data link layer encounters 5 consecutive ones in the data, it automatically stuffs a 0 bit into the outgoing bit stream. So I think it will be clear by taking an example. Then after we will come to this theory part. So this is the thing. So here suppose this A, the message that is shown as A, is what is being the sender is trying to send to the receiver. So the data link of sender will see this particular frame as a whole. See, to this frame as a whole, it is going to attach that special start of frame delimiter and end of frame delimiter, particularly that 0 followed by 6 ones and a 0. So that will be attached at the beginning of the frame and also at the end of the frame. So now see, whenever the receiver is encountering 0 followed by 6 ones followed by 0, it will realize it as the means. So suppose it started reading by seeing the start of frame delimiter, then when it keep on reading, whenever it encounters 0 followed by 6 ones followed by 0, it will treat it as end of the frame delimiter and it will stop reading at that point. But it may not be the actual end of delimiter. It may be something that occurred as part of the original message. So how we can resolve this issue? In the original message, whenever we are having a chance of getting, say, such a pattern like 0 followed by 6 1 followed by 0, we will not allow this kind of a pattern. So we have a common rule. So the rule is like this: at the sender side, whenever the sender sees 0 and 5 ones, okay, so whenever the sender at the sender side, whenever the sender encounters 5 consecutive ones, right, particularly 0 followed by 5 consecutive ones, it is going to be the pattern. So I don't want this to be a pattern. So after 5 ones, what will be the next bit, whether the next bit is 1 or 0, I have a common rule. So whenever in the original frame, if I encounter 5 ones, following that 5 1, I will be simply attaching a 0. So that if it is leading to the pattern like a 0 followed by 6 1, I will not let that pattern occur, because 0 followed by 5 1, then I am attaching a 0, so that at the receiver side, it can clearly understand that this is not the special end delimiter pattern, because end delimiter pattern I need 6 ones, but here 5 1, whether the sixth bit is 1 or 0, I will be attending that, appending that or stuffing that 0 in between. So actually it is like a 0 followed by 5 1, then only it is enough for you to append a 0, but in HDLC, for simplicity, we are just considering all the 5 consecutive ones occurrence. Following that, we will be stuffing that 0. So that is the idea used here. So it is like this is the original message that we want to send. So say start reading from this side. This is the first bit being sent by the sender. 0 followed by 2 1, no issue. 0 followed by not 0, consecutive occurrence of 5 ones, and they are stuffing. So 1 1 1 1 5 1. After this fifth one, a 0 is stuffed. That is this 0. Then again another 5 ones. After that, a 0 is stuffed. Another 5 1, after that a 0 is stuffed. This is the last one. Maybe if you count here, there will be 16 ones, I think so. 4, then 4, then 4, 16. So that is why 5 ones, then a 0, again 5 1, then a 0, again 5 1, then a 0. So totally 15 1, and then the last 1. So this is how those 16 ones were treated. In between 3 zeros were stuffed, and it will be sent to the receiver side. Now what will be the rule that is applying, that will be running by the data link layer of the receiver side to handle this flow? I mean frame synchronization. It will keep on reading, and whenever it is seeing that 5 ones, the sixth bit it will check. If the sixth bit is also 1, then it could be the end delimiter pattern. Now if the sixth bit is not a 1, if it is a 0, definitely it is the one that is being attached by the sender. So that one 0 will be removed. Again it will continue reading. It will keep a counter, say 5 ones were there. So what is the sixth bit? It will check that sixth bit. If it is 1, say followed by a 0, it will be treated as end of frame delimiter. But in the normal message, such a case will never occur, because whenever there is 5 1, a 0 will be stuffed by the sender. So that stuffed 0 will be removed by the receiver, and so that the result will be interpreted as what is sent by the sender originally. So the idea is simple. I hope just try to reread and understand by yourself. If you have any doubts still, or you can ask me when we are having the live discussion session. Okay. And now the thing is that what you have to keep in your mind, it is not like a 5 1 followed by a 1. So we are not trying to break this pattern. If the sixth bit is 0 also, with this stuffing will do, because we have a common rule. Whenever there is 5 1, I will stuff a 0. At the receiver side, whenever 5 ones are received, sixth one it will check. If it is 1, then it will wait for one more bit. Accordingly, it will determine it as the end delimiter pattern. If the sixth bit is 0, definitely it will be removing that sixth bit, because it will be the one being stuffed by the sender. Now what about the seventh bit, whether it is 1 or 0, that will be taken as the data, part of the data. Okay. And why we are stuffing a 0 after 5 continuous occurrence of 1? Because our delimiter pattern is 6, containing 6 consecutive 1. And the same thing you can come up with a different solution, where if you want in HDLC, this is particularly what we are using, but you can have a delimiter pattern, maybe 0 followed by 10 ones and a 0, for example. In that case, what will be the where you will be doing that stuffing? After 9 consecutive 1, then only it's enough for you to stuff the 0. But actually, to break this pattern, you can stuff a 0, say at any position, right? Why we have to wait for 5 ones? There is an answer to this. I just left as a brain exercise for you. So just think about situation. My question is like the original pattern, I mean delimiter pattern in this particular example, HDLC is 0 followed by 6 1 followed by a 0. Now to break this pattern in the actual frame message, this pattern you can break by stuffing a 0 maybe after the first one or the second one. at any position definitely the pattern is going to be breaked, but why we are stuffing as 0 only after the fifth one? If there are 6 consecutive ones in the original pattern, so suppose instead of this 0 followed by 6 1, suppose our pattern is like 0 followed by 10 1 and then a 0. If that is our pattern, then the how we will be stuffing 0 after the every occurrence of 9 consecutive ones, a 0 will be stuffed, and accordingly it will be removed by the receiver. So the protocol is clear for you. Now the question is, why it is we have to wait till 9 ones? Why don't we break the pattern by stuffing a 0 say after 5 ones, something like that? So that you think by yourself, and when we are having the live session, try to answer me. So that about it. And now see what we have read so far. It's about the center side. It will be stuffing a 0 after 5 consecutive ones. Now this USB is also using a similar bit stuffing technique. So when the receiver sees 5 consecutive ones, the incoming 5 consecutive incoming 1 bits, the definitely the one followed by it will be 0, provided it is the original message, and that 0 will be removed, that it destuffs by the receiver. Now if the user data contain the flag patterns, this one, this flag will be transmitted as say 0 followed by, so here it is taken a different no, the same flag, right? This will be followed as, yeah, the flag if the data contains the same flag pattern, definitely that flag pattern will be followed by stuffing a 0 after 5 ones. So this is something different, right? So the receiver will not be confused with this pattern as the end delimiter pattern. So but stored in the receiver memory by removing this as the original data, like this. So with bit stuffing, the boundary between two frames can be unambiguously recognized by the flag pattern. So it is a very clear forward method, and just a 0 stuffing instead of a byte stuffing, just a single bit stuffing. So the size of the message is also not going to increase much, but still the number of bits to be appended proportional to length of the message only. That problem is still there. Thus, if the receiver loses track of where it is, all it has to do for checking for a flag, the flag sequences, since they will occur only at the boundary part. So whenever there is 0 6 1 0, definitely it is going to be star end of the current frame. So like that it can resynchronize at any point without the overhead of stuffing a byte, just enough to stuff a 0, I mean a single bit. Yeah. Now the fourth method, so that is a pretty good method out of the 3 methods that we discussed. Now we will see one more technique, that is a physical layer coding violation. So what does it mean? So with both the bit stuffing and byte stuffing, the side effect is that the length of the frame now depends on the contents of the data it carries. So compared to byte stuffing, bit stuffing is better in the sense, instead of stuffing a byte, we are stuffing just a single bit, but still how many bits you are going to stuff, that will be proportional to length of the frame, maybe length of the frame divided by size of the pattern in worst case, right? So that is the thing. So if we need an independent method, we can, I mean a solution that is independent of length of the message, some constant value you want to append, and you just want to make the frame delimiter pattern, then you have a choice. So the method is like before that method, so some problems of this bit stuffing and byte stuffing were highlighted. For example, the original message is of 100 byte, and without any stuffing, those 100 bytes will be sent as 100 bytes only, maybe with the special flags. Now with the stuffing, what will happen in worst case, for 100 byte we may be forced to append 100 more byte. In the sense, assume that all those 100 bytes are either that escape pattern or a flag, that special flag pattern. Such a message can occur in worst case. Okay, so in such a situation, very rare, but still if such a situation occur, we should be ready to handle. In that case, with every occurrence of the byte, as it is either the escape byte or the flag byte, we will be appending one more escape byte. So totally the size of the new message that we are sending will be 200 bytes. So out of this 200 byte, only 100 byte is useful. So it is like some 50% efficiency, I mean overhead you can see in this case. But in case of bit stuffing, instead of that 50% increasing size, I mean overhead, here it will be only 12.5 percentage overhead. Why you are getting 12.5 percentage? Because just look at the pattern. If the special pattern is some 8-bit pattern, whenever that 8-bit sequence is coming, say 100 divided by 8, it is roughly this 12.5, right? So for every 8-bit pattern, say maximum 1 bit is stuffed extra instead of 1 byte. So the overhead message is like this 12.5 percentage, and out of 100, 12.5 means for every 8 special flag pattern, if it is occurring in the original message, we have to break it by appending a single bit. So 12.5 percentage still inefficiency you can see, in the sense 12.5 percentage is just overhead stuffed bits only, and those bits has to be removed at the receiver side. So it is far better compared to byte stuffing. Instead of 50 percentage wastage, now we have 12.5 percentage wastage only, but still we have that 12.5 percentage, means for 100 byte it is 12.5, it is proportional to size of the message. If it is 1000 byte, then it will be 125, like that it will go, right? So the last method, so that is a kind of a solution that is independent of the length of the message, is what we are doing. We are depending on some shortcut from the physical layer. The encoding bits are going to help us so to achieve redundancy. For example, see this the 4B bar 5B encoding that we might seen in our when we studied the data communication during that encoding technique. So what the sender will be doing, every 4 bits will be converted to some 5-bit pattern, some kind of using some mapping table, and those 5 bits they will be encoded using some signal. Right, so why such an encoding? So the encoding of bits as signals often includes some redundancy. So this one extra bit is actually the redundant bit to help the receiver. So the redundancy means that the signal that some signals will not occur in the regular data. So for making our encoding and its decoding part easier, we did some such a we added some kind of redundancy in the physical layer. So 4 bits using a mapping table, we will map to 5 bits, and those 5 bits will be converted into signal. So that kind of line encoding technique is used in many applications. So in that case, so what will happen, the 4 bits 4 data bits are mapped to 5 signal bits to ensure sufficient bit transition. So that is something for that encoding we are using this. But now what we are going to do is, every 4 bit will be mapped to 5 bits. Now using 5 bit, how many combinations are actually possible? 32 combination. But using 4 bit, only 16 combinations. So for those 16 combination, we need some 16 5 bit combination from the 32. So remaining 16 are actually unused. So that is a thing you have to highlight. So this means that 16 out of the 32 signal possibilities are not used. So using 4 bit 16 combination, those 16 combination, some 16 mapping you can provide with 5 bit combination, but what about remaining 16 combination, that will be unused. And those unused combination, we have a clarity that it is never going to occur in the original message, because they are unused ones, right? And this is normally gated by some kind of table on the background, and this all those 5 combination which are listed in the table only will be used for creating the original frame, so or its encoding part, the remaining pattern. So this is something known to the physical layer only. Now the data link layer will be communicating with the physical layer, and it will be taking those the 16 unused combinations of 5 bits, and any of these combination can be used as the start of the frame delimiter and end of the frame delimiter. So you are now very clear about the fact that this pattern is definitely not going to occur in the original message, because the type of signal encoding technique we are using is 4B by 5B, where the table is showing this many combination to be used for this many, and the remaining unused combination you are not going to get as part of the original message. So simply you can append them without worrying about its occurrence in the original pattern, and you don't have to stuff anything. So it is a very good solution without any stuffing at all. So but we can use it only in cases where this 4b bar 5b kind of encoding is used. So we can use some reserved signal to indicate the start and end of the frame. So this is in effect we are using some kind of coding violation to delimit the frame. So as per the coding rule, 16 combinations were valid, and we depend on some invalid combination, so or we gone for coding violation to frame the to locate the start and end of the frame. So the beauty of this scheme is that because they are reserved signals, it is easy to find the start and end of the frames, and there is no need to stuff any data. So it is fully stuffing free. So that is also proposed as a fourth method in literature, and you can use it of course with encoding technique like 4b or 5b, but in all cases it is not going to work fine. So framing in Ethernet and 802.11. So just to get a practical view, I listed this because even though we studied those four combination, four different types of framing technique, in most of the practical protocols you will be seeing slight variation of this technique, and maybe more than one techniques mixed together. So many of the data link layer protocols that we are practically using, they use a combination of these methods for safety. For example, if you look at Ethernet, IEEE 802.3 standard or IEEE 802.11 Wi-Fi wireless LAN, what they are doing is what they used to have is they have a frame begin with a well-defined pattern called a preamble. So that special pattern by which the frame started or which act as a frame start delimiter pattern is having a special name called a preamble, and this special pattern is of long enough, quite long, in the sense what we seen already as an example is just that HTLC 0 followed by 6 1s or something like that, smaller 1 byte length pattern. But in when it comes to practical protocol like Ethernet 802.1, for more robustness what we are using is some very lengthy preamble special pattern attached at the start of the frame delimiter, so typically 72 bits in 802.11, to allow the receiver to prepare for an incoming packet. And yes, this pattern 72-bit pattern, so it will get enough time for synchronization. Nicely it will synchronize with the sender, and the preamble is again followed by length of the frame, that is the count. So the byte count method and bit stuffing, or byte count method and byte stuffing, like that the combination is being tried here. So this is not like actually you should not confuse it with bit stuffing or byte stuffing. It is a different method. Here actually the technique is byte count only, byte count or length method only, but byte count itself may be erroneous, right? And whenever the byte count is as the byte count is error prone, whenever it some error occur in the byte count, we should not be confused, in the sense that some example we already seen where the frame is going to is facing difficulty in synchronization and it go out of resynchronization, and that time you can depend this special preamble pattern, the 72-bit preamble pattern. So if the count fails, this preamble will help you, but in worst case if both fails, still it's a problem. But as error probability is very less in Ethernet and all, this is working nicely. And of course in 802.11 also. I think in this bit stuffing, other than HDLC, it is the technique being used in token ring local area networking framework also. So that about it. Yes, with which we will end up the discussion. So the technique of framing we discussed were byte count method and special flag byte with byte stuffing, and special flag bit pattern with bit stuffing, and finally the coding violation. And what is the case with the Ethernet or 802.11, whether we have a special bit pattern called preamble and also that count, both we are using. So that about it. Thank you, and in upcoming session we will see more on the other design issues of data link layer. Thanks for watching.